Before inclined planes, we learned about the force of gravity in free body diagrams, acting on objects sitting on a horizontal surface or in free fall. I'm going to draw these two examples here. Here I'll draw a horizontal surface for us to place an object on, and here I'm going to draw a vertical surface for the sake of this discussion. So I'm going to place my object here on this horizontal surface. In the example of free fall, I'm going to put it on this against the wall here, just as a comparison. So the force of gravity in the first example, of course, acts straight down. And here again, it acts straight down. In this example, the force of gravity pushes the block into the surface, resulting in a normal force. In this example, the force of gravity is pushing the block straight down, not into the surface. So this force of gravity results in an acceleration, and so the force of gravity is the net force acting on this object. So let's say that the force of gravity here happens to be 100 newtons here. Then we can say that in the first case, the normal force is 100 newtons. And in this case, the net force is 100 newtons. This block is going to have an acceleration due to its net force. This block has a net force of 0 because the force of gravity and the normal force balance each other out. Now, we can think of this as a 0-degree incline, this level surface. And this can be thought of as a 90-degree incline here. So what happens in between? We can have a surface like this that is at an angle. Let's pretend that this angle here happens to be a 45-degree angle. What happens when we place our object on this surface? This is our inclined plane. So the force of gravity still acts downwards here, but now it's doing both things. It's both pushing the block into the surface, like in this example, and it is accelerating it down the incline, like in this example. So this force of gravity is going to be divided into two parts. One part acting this way, and one part acting this way. We call the part that pushes the block into the surface the perpendicular component of gravity because it is perpendicular to the surface. And we're going to call this force of gravity that is parallel to the incline the parallel force of gravity. So we can now remove this force. So we've divided gravity up into its components. And just like here, the part of gravity that pushes into the surface is going to result in a normal force. So we're going to have a normal force here. That will be equal to Fg perpendicular. And then we have Fg parallel, which is going to be, in the absence of any other forces, equal to the net force. So I can say that the net force here is equal to Fg parallel. And so we're going to look at how to exactly find out the values of these components of gravity. So we add here. This is our 45-degree angle. So we have the two extremes, 0-degree incline and 90-degree incline, where gravity is just doing one thing. It's either pushing the object or block into the surface, or it's causing it to accelerate along the surface. And every angle in between, we're going to have a diagram like this. So let's see how we're going to find out the values of the components of gravity. So I'm going to draw another incline here. And this is going to be at some unknown angle, theta. Here's our block. And for easy geometry, I'm going to draw the center of mass and the free body diagram from this point here. And I'll draw the force of gravity like this, so that we have a line here that creates this right triangle. So this is our force of gravity, Fg. We can split this now into the two components that we saw earlier. There's going to be a perpendicular component that's going to come down to this point. So we call this FG perpendicular, and there's going to be a parallel component that's going to be drawn out to here. And this is our FG parallel. This force of gravity parallel can also be drawn in here to create this nice right triangle. So I'll label this as well as FG parallel. So what are the values of FG perpendicular and FG parallel? To determine that, we need to know what is the angle inside this right triangle. So here we have a right triangle. We need to know what is this angle. Turns out that this angle is equal to the angle of the incline theta. So this is angle theta. Because theta is complementary with this angle, and because this is also a right triangle, these two angles are complementary. Let's call this angle beta. So let's say if this angle here was 30 degrees, then angle beta would be 50 degrees. Because these two angles are complementary, then angle theta must also be 30 degrees, the same angle as the incline. Now that we have our right triangle with known angle, we can solve for the different sides of this triangle, given that we know what the force of gravity is. So I can maybe redraw this triangle here. So we have this hypotenuse is the force of gravity. And then we have FG perpendicular here. We have FG parallel here. Because our angle theta is here, and this is the right triangle, that means that FG perpendicular, which is adjacent to the angle, is going to be equal to the hypotenuse times the cosine of the angle, FG cosine theta. And FG parallel, because it is opposite to the angle, is going to be equal to FG sine theta. So this is how we solve for the values of FG parallel, FG perpendicular. Okay, so in the absence of any other forces, the normal force acting on this block, which is also perpendicular to the surface, is going to be equal to FG cosine theta, or I can write it as mg. Mg is equal to the weight, mg cosine theta. And the parallel component of the force of gravity is going to be equal to the net force. So the net force on this block would be mg, which is the weight, times sine theta. So let's look at some examples here. So I've set up here 4 inclines at different angles. We're going to say that these are all the same blocks. So I have a block, let's say, of 10 kilograms. We'll make the acceleration due to gravity 10 meters per second squared. So that means that the force of gravity, the weight of the block, which is m times g, 10 times 10, is going to be 100 newtons. We're also going to give these surfaces some friction. So let's say that the coefficient of static friction is equal to 0.8 and the coefficient of kinetic friction equals to 0.5. So let's start analyzing these diagrams. So all these are going to have parallel and perpendicular components. I could just draw the force of gravity for all of these like this, but I'm gonna have to resolve them anyway. So let me go ahead and draw the components instead. So I'm gonna have a perpendicular component here, FG perpendicular and FG parallel. And I can solve for those using my calculator. We saw before that FG perpendicular is going to be the weight times cosine of the angle. So here, the weight of my block is going to be 100, and the angle is 20. So 100 cosine 20 will give me my perpendicular component. I can use my calculator. 100 newtons times cosine of 20 will be, to write 100 times cosine of 20 will be 93.4 newtons. And the parallel component will be 100 times sine of the angle, 100 times sine 20. And that will be 34.2. 34.2 newtons. From this, I can now draw in my normal force. I know my normal force will be equal to the perpendicular component like this. So here I have a large normal force of 93.4 newtons. And because I have a normal force and I have a coefficient of friction, we're going to have a force of friction. So we're going to calculate the force, the maximum force of static friction by using the equation force of friction static is equal to mu static times normal force. That's going to be equal to 0.8 times 93.4. 0.8 times 93.4. So we have a maximum force of friction of 74.7, which is greater than this. So I'm going to draw my maximum force of static friction here as a dotted line. Force of friction max is equal to 74.7 newtons. So there's more than enough friction to hold this block in place, which means that right now the current force of friction is just going to be equal to the parallel component of gravity. So the force of friction is 34.2 newtons. Having a maximum force of static friction that is greater than this just means that if I were to come along and try to push this block down the incline like this, there's enough friction to stop me from doing that. Unless I push with a force that's going to result in a sum larger than this, the block will not slide down the incline. All right, so we completed our diagram here. And I can say now the net force in this example, the net force here is equal to 0 newtons. Because the perpendicular component of gravity cancels out with the normal force, and the parallel part of gravity cancels out with the force of friction. Alright, so we'll do the same thing now for the rest of these. I have to draw in here a perpendicular force of gravity and a parallel force. This time the angle is 30, so let's do our calculations. 100 times cosine 30 and 100 times sine 30. So we're going to have 86.6 and 50 newtons. Of course, that means our normal force is going to be equal to the perpendicular component of gravity. So Fn equals 86.6. This then determines my maximum force of static friction. So force of friction max will be equal to 86.6 times 0.8 like we did before. 86.6 times 0.8. And we get a maximum force of 69.3. So because the force of gravity parallel is less than that maximum force, I know we have enough friction to hold this block in place. So I can draw the force of friction here is currently 50 newtons. And again, we end up with a net force of 0 in this scenario. But of course, as we tilt the incline higher and higher, eventually this block will begin to slide. And that's probably going to happen here. So let's find out what our forces of gravity are. We're going to have a perpendicular component and a parallel component. The angle now is 40 degrees. So when I do my calculations, we'll have 100 times cosine 40 for the perpendicular component and 100 times sine 40 for the parallel component. So we have 76.6 and 64.3. Because I have my perpendicular component of gravity, I know the normal force is going to be equal. And using this and my coefficient of static friction, I can find out what the maximum force of static friction is. That'll be 76.6 times 0.8. 76.6 times 0.8. And that is 61.28. 61.28. So that's less than, if I try to draw this in 61.28, this is less than the force of gravity parallel, so the block will begin to slide here. So this is no longer a static friction example. Now we're going to have a force of kinetic friction. The force of kinetic friction is equal to mu k times normal force. Right, so we saw that there's not enough static friction to hold this block in place. It is going to accelerate. You have to find out what is the coefficient, what is the force of kinetic friction. So I'm going to use 0.5 as my coefficient when doing my calculation. 76.6 times 0.5. And the force of friction is 38.3. So this block is accelerating down the incline. There is a net force acting on it. So the net force here is going to be equal to the difference between Fg parallel and the force of kinetic friction. Yeah, this is kinetic force of friction. So that's 64.3. 64.3 minus 38.3. We have a net force of 26. The net force will be 26 newtons. And we can use that to find the acceleration if we wanted to. We can take the net force, acceleration is equal to net force divided by mass, 26 newtons divided by the mass of 10 kilograms. We'll get 2.6 meters per second squared for the acceleration. So now that we know at this angle of 40 degrees the block accelerates, it's also going to accelerate at 50 degrees. So let's go ahead and just finish this example. I'm going to have a force of gravity perpendicular here and a force of gravity parallel. For the first time now we're going to have a parallel component that's going to be greater than the perpendicular component because we've gone at an angle. We're not at an angle above 45 degrees. So let's go to our calculator. 50 degrees, 100 times cosine of 50, and 100 times sine of 50. So it's going to be the same value actually here, because these angles are complementary. These two numbers just swap. So 64.3 is now our perpendicular component, and 76.6 is our parallel component. So we have an even smaller normal force, right? Every time we increase the angle, the normal force gets smaller and smaller. 64.3. So we're going to have an even smaller force of kinetic friction here. The force of friction is going to be equal to 64.3. 64.3 times the coefficient, which is 0.5. And we get 32.15. And again, we can solve for the net force. The net force in this example is going to be equal to 76.6 minus 32.15. We get 44, let's call it 44.5. Okay. So the block began to slide somewhere between 30 degrees and 40 degrees. And a very common question in inclined planes is, at what angle does that happen? So here's a sample question. We have our 10 kilogram block is on a horizontal surface. The coefficient of static friction is 0.8, like we had before. The coefficient of kinetic friction is 0.5. The surface is then tilted. At what angle does the block begin to slide? So this is going to be our unknown here, angle theta. What is this going to be? So of course on an inclined plane, there's going to be a force of gravity perpendicular. There's going to be a force of gravity parallel. We're going to have a normal force that is equal to Fg perpendicular. And for this question, we want it to be such that the force of gravity parallel is equal to the maximum force of static friction, because any angle above that and the block begins to slide. So force of friction max. So to solve for this angle, we're just setting this and this equal to each other. So we'll do that here. We want Fg parallel to be equal to Fg force of friction max. So we know Fg parallel is equal to mg sine theta. Force of friction max, well, this is equal to mu static times normal force. But the normal force on this inclined plane, normal force is equal to Fg perpendicular. Fg perpendicular is mg cosine theta. This is also mg cosine theta. So force of friction max is mu s times mg cosine theta. This is this. We see that here. So it's going to be mu static times mg cosine theta. Now we just do some algebra. The mg cancels out on both sides. We get mu s is equal to sine theta over cosine theta. Sine theta over cosine theta is tan theta. So then solve for theta. Theta will be equal to the inverse tan of the coefficient of friction, mu s, and the inverse tan of our coefficient of static friction, which is here, is going to be second tan 0.8, and we get 38.66. And that's to be expected. We saw in our problem that the block did not begin to slide at 20 degrees. It did not slide at 30 degrees, but somewhere between 0 and 40, the block begins to slide. And that matches our result here of 38.66.